Right now, Google is paying almost $1 billion a month just to rent silicon chips. Think about that capital expenditure for a second.
Yeah, it's staggering.
Nearly $1 billion every 30 days. And, that's not to build a new product or, hire engineers. It's simply to secure the raw computational power required to just stay in the game.
Right, just to keep the lights on, essentially.
Exactly. And yet, an infrastructure company you've probably never even heard of just hit a $13 billion valuation today. And they did it by figuring out how to out-engineer those massive hyperscalers using custom C++ code. And this is the crazy part, a wild, borderline science fiction pitch to dam rivers in the Himalayas.
It sounds completely made up, but the math is very real.
It is. Today is Monday, June 22, 2026, and we are taking a deep dive into the absolute bleeding edge of the AI industry.
The company we're looking at is Baseten. And that $13 billion Series F valuation they just closed today, it's fascinating because they operate entirely in the shadows.
Right, they aren't the ones making the big flashy announcements.
Exactly. They don't build the frontier models that make the headlines on Twitter. They don't have a consumer-facing chatbot that you or I would use. They handle the brutal, unglamorous, and frankly, violently expensive reality of what happens the moment a user actually presses enter on a prompt.
We're talking about inference.
Yes, inference, the actual execution of the model in real time.
And we've got an incredible set of sources for this deep dive. We're pulling from tweets by Baseten's leadership, some insanely detailed technical breakdowns of their software stack, and this fascinating manifesto and roadmap titled Netizen, Baseten's Path to $1 Trillion by Paramendra Kumar Bhagat.
That document is just incredibly dense.
It really is. And the mission for our deep dive today is to unpack all of this. We want to show you the hidden machinery of the AI boom. How does a company plan to go from $13 billion today to $1 trillion in 10 years? And why should you, as the listener, care?
Well, you should care because right now, every single time you use an AI app, you are participating in a massive bottleneck.
Right. You are demanding compute power that honestly barely exists. If you want to understand where the tech economy is actually going, you have to look past the flashy AI models and look at the digital plumbing.
The digital plumbing is where the actual war is being fought. And looking through Bhagat's roadmap, what stands out immediately is this massive shift in enterprise behavior. We aren't just in an AI bubble anymore.
No, we are in an inference bottleneck.
Exactly. You look at companies like Notion or Cursor, Abridge, Hagen. For the last couple of years, the standard playbook was, well, it was easy. You just ping OpenAI or Anthropic's API.
You just rent the intelligence.
Right. But Basen's CEO, Tuhin Srivastava, is pointing out that this architecture is collapsing under its own weight. He calls the new paradigm owned intelligence.
Owned intelligence. So it's like, okay, relying on closed APIs is basically like renting a furnished apartment, right? It's super easy to move in, but you can't knock down a wall. And landlord can just double your rent overnight.
That's a great way to put it.
So owned intelligence is building your own house.
Ah.
But, I have to push back here a little. Isn't building your own AI infrastructure incredibly exhausting? Like if I'm a startup and I just want to build a cool app, I don't want to become a server management company.
It's a total nightmare. The engineering overhead required to serve a 70 billion parameter model to millions of concurrent users without the servers literally melting down is an entirely different discipline than just building a SaaS application.
Right. You need kernel engineers, you need hardware allocation specialists.
Distributed systems experts, yeah. And that is the exact friction that Baseten is monetizing. They are stepping in to be the universal inference fabric.
So they do the hard part for you.
Exactly. Startups want the control and the unit economics of hosting their own models, but they do not want to build a DevOps team to manage GPU clusters. Baseten abstracts all of that away, and they guarantee 99.99% uptime.
Which is wild. And their inference business grew 20x in the last year alone.
Yeah.
Because I guess training a model is a one-time thing, right? You spend $1 billion once, but inference.
Inference is a perpetual, infinite operating cost. It scales linearly with your user base. Every single time a user asks a question, that costs you compute.
And the margins on that infinite cost have to be razor thin, which is why Baseten had to engineer a software stack that shaves off microscopic fractions of a second to save their clients millions. So let's look under the hood. The technical breakdowns in these sources are just absurdly detailed.
They really are. They aren't just spinning up generic AWS instances. The sheer hostility of the inference environment requires custom engineering.
Right, because the bottleneck isn't usually the compute itself, is it?
No, it's memory bandwidth. When we talk about serving large language models, we are fundamentally limited by how fast we can move data from the GPU's high bandwidth memory, the HBM, into the actual compute cores, the SRAM, to do the math.
So let's get into how Baseten bypasses that memory wall. The sources talk about kernel fusion. And I was reading this, and so if Bayesian is bypassing the industry standard, they must have found a massive inefficiency, right?
Well, Triton is a generalization. It's designed to be flexible and accessible for researchers so they don't have to write low-level machine code.
Right.
But flexibility always introduces overhead.
Okay, so what does that overhead look like in practice?
So if a neural network needs to perform a sequence of operations, say a matrix multiplication, and then it adds a bias term, and then it applies an activation function like a SILU, a standard compiler will launch 3 separate GPU kernels.
3 separate instructions.
You're right, meaning the compute cores have to fetch the massive weight matrices from the global memory, do the multiplication, write the intermediate result back to the global memory, and then immediately read that exact same result back into the cores for the bias addition.
Oh, wow. So the data is just commuting back and forth endlessly.
Endlessly, and every single one of those trips to the global memory takes hundreds of clock cycles. It is devastating to your latency.
So kernel fusion is fixing that commute.
Exactly. It's the incredibly painful process of writing low-level C++ code to combine those operations into a single kernel.
You do it all at once.
Yes. The data is loaded into the hyperfast local SRAM once. All 3 mathematical operations are performed consecutively right there on the chip, and only the final result is written back to the global memory.
That makes so much sense. You are drastically reducing the memory bandwidth requirements. But, I mean, there's a physical limit to how much you can optimize that transfer, right? You can fuse the kernels to stop the commuting, but eventually you hit a wall.
You do. You just can't make the commute any faster.
So to get more speed, you have to make the actual cargo lighter.
Shrinking the cargo, that's the perfect way to visualize it.
And this brings us to quantization. The roadmap goes heavy into their use of FP8 and FP4 formats, especially on the new NVIDIA Blackwell GPUs. Can you explain that?
Sure. So traditionally, neural networks parameters are stored as 16-bit or 32-bit floating point numbers. That's a massive amount of data to shuttle across the memory bus for every single word the AI generates. Quantization compresses those numbers down to 8 bits, or in the extreme case of FP4, just 4 bits.
But wait, if you compress the numbers that aggressively, if you just crush a 16-bit number down to 4 bits, aren't you just mathematically lobotomizing the model? Like, wouldn't the AI just start hallucinating or spitting out garbage?
That was the assumption that dominated the field for years. Everyone thought you'd destroy the model's perplexity.
But you don't.
No, because advanced post-training quantization algorithms have proven it wrong. Methods like AWQ, activation-aware weight quantization, they don't just uniformly round all the numbers.
Oh, so it's smart compression.
Exactly. They analyze which specific weights are most critical to the model's output distribution, and they preserve those important weights at a higher precision. Then they aggressively compress the less important ones.
That's brilliant. So what's the end result of that?
The result is a model that is a quarter of its original size and memory, but it retains like 99% of its original capabilities.
Wow. And because it's a quarter of the size, you can fit a massive 70 billion parameter model on way fewer GPUs. Or you can process batches that are 4 times larger on the hardware you already have.
Which is an insane multiplier on throughput, especially with the new Blackwell chips, because they have native hardware support built directly into the silicon to accelerate those specific FP4 calculations.
Okay, so that ties directly into how they handle continuous batching. Because if you're freeing up all this memory by shrinking the cargo, you need a system that can constantly keep the GPU fed with user requests, right?
Right. The old paradigm of static batching is basically dead for large language models.
Because generation is autoregressive. The model spits out one token at a time, and every user asks for something different.
Exactly. If you batch 20 prompts together and one user asked for a quick sentence, but another user asked for a massive Python script,
then 19 slots on that GPU are just sitting idle. They're locked up waiting for the Python script to finish before a new batch can load. That seems so inefficient.
it's terrible for utilization. So continuous or in-flight batching operates at the iteration level rather than the request level.
Think of it like a high-speed commercial kitchen.
Yes. The moment a chef finishes chopping onions for one dish, the ingredients for a completely different order are slid under their knife. The blade never stops moving.
So as soon as a user's prompt emits its final word, a new user's prompt is seamlessly injected into that exact memory slot for the very next fraction of a second.
Seamlessly. Frameworks like TensorRT LLM manage this orchestration, and it ensures the GPU utilization stays pegged near 100%.
But the orchestration gets even wilder when we look at speculative decoding.
Oh, speculative decoding is fascinating.
It's probably my favorite mechanism we've looked at today because it fundamentally alters the physics of how these models generate text.
It really does.
Because standard generation is strictly sequential, right?
Okay.
The model has to calculate word 1, then use word 1 to calculate word 2. You literally cannot parallelize the future.
You can't. But speculative decoding introduces a second, smaller model into the mix, a draft model, and it uses it to cheat the sequence.
It's brilliant. So you have a massive, slow target model and a tiny, incredibly fast draft model.
Right. It's an exploitation of compute asymmetry. The tiny draft model runs ahead, generating a speculative sequence of, say, 5 tokens almost instantly.
It's like a brilliant executive having a junior assistant. The assistant rapid fires a draft of an email. It might be slightly wrong, but it's really fast.
And here's the mechanical genius of it.
Yeah.
The large target model, the executive, can take those 5 drafted words and process them all simultaneously.
In a single forward pass.
Yes, in a single forward pass. To verify their accuracy against its own probability distributions, the executive just quickly stands and signs off on it.
Which is vastly faster than the executive typing it out themselves.
Exactly. If the draft model guessed correctly, you just generated 5 tokens in the time it usually takes to generate one.
But what if the assistant messes up? What if the draft model gets word 3 wrong?
Then the target model accepts the first 2 words, rejects the rest, outputs the correct third word itself, and the draft model just starts guessing again from that new point.
That is so smart. And I imagine for stuff like code generation or highly structured outputs like JSON, that draft model is going to guess the boilerplate syntax perfectly almost every time.
Almost every time. You are effectively doubling or tripling your token emission rate without sacrificing a single ounce of the large model's mathematical precision.
Because the final output is mathematically guaranteed to be identical to what the big model would have produced anyway.
Precisely. But, you know, as fast as you make the generation, the most severe bottleneck for enterprise applications isn't actually generating the token.
It's absorbing the prompt.
Yes, the prefill phase. And this brings us to KV cache optimizations, specifically their implementation of radix attention.
Okay, let's break down the KV cache, because this is where the memory footprint just explodes. When you, as a user, drop a 50-page PDF into an AI and ask a question about it, the model has to process all 50 pages to generate the mathematical context before it can even begin to answer you.
And those are the keys and values. Standard attention mechanisms scale quadratically, which means the longer the context, the exponentially heavier the computational load.
And if that user asks a follow-up question like, okay, now summarize page 4, a naive system has to recalculate that entire 50-page PDF all over again, just to remember the context.
Which is a massive waste of compute. So the key value cache solves this by storing the mathematical representations of the previously processed tokens in the GPU's memory.
But managing that cache across thousands of concurrent enterprise users, that has to be a routing nightmare.
It is, and this is where radix trees come in. Imagine an enterprise has a massive internal system prompt, say a 10-page document outlining the company's specific coding guidelines. Every single employee interacting with the internal coding assistant is sending that exact same 10-page prefix with every single prompt.
So a standard KV cache would store a separate copy of that 10-page prefix in memory for every single employee.
Yes, it wastes gigabytes of precious VRAM.
Wow.
But by structuring the cache using a radix tree, the Baseten runtime maps the exact sequence of tokens. When employee A and employee B share the same system prompt, the tree points both of their sessions to the exact same physical memory blocks on the GPU.
Oh, that's incredibly elegant. It only branches off and allocates new memory when their individual conversations diverge.
Right. It's called prefix caching and cache-aware routing. The load balancer sees an incoming request from an employee, it checks the hash of their system prompt, and it instantly routes their connection to the specific physical server rack that already has that exact prompt warmed up in its local memory.
So it drops the time to first token from seconds down to milliseconds.
Exactly. When you compound all of these mechanisms, bypassing Triton with custom C++ kernels, shrinking the footprint with FP4 quantization, parallelizing the generation with speculative decoding, and sharing memory with radix trees, You really begin to understand how a company achieves a $13 billion valuation just on infrastructure.
They are mathematically extracting more yield out of the silicon than the hyperscalers are.
They absolutely are.
But, shaving off milliseconds and extracting yield from silicon today is very different from capturing $1 trillion of enterprise value over the next decade.
It's a completely different game.
Right. And Bhagat's manifesto lays out a deeply aggressive, highly specific, three-phase roadmap for Baseten to hit that $1 trillion mark by 2036. And I really want to scrutinize the mechanics of this because drawing a line on a graph that goes up to $1 trillion is easy. Surviving the market dynamics to actually get there is brutal.
It's extremely brutal, and the timeline in the source document is highly compressed.
So let's look at phase one. This covers 2026 to 2028, and it's titled Dominate Inference.
Right. The goal here is establishing the inference fabric. They want to be the default API for any workload, whether it's running in Baseten's cloud, in a customer's virtual private cloud, or even on bare metal servers on-premise.
And the financial target for phase one is $2 to $5 billion in annual recurring revenue, aiming for a 2028 IPO.
Right.
But there's a massive anomaly in the manifesto's projections here.
Yes, there is.
The document explicitly states phase one targets a $5 to $10 billion valuation. Yet, as we established at the start of the show, today's Series F just priced them at $13 billion.
Which means they have shattered their own upside case 2 years early.
Right. How does that happen?
That anomaly is a perfect indicator of the broader market distortion we're seeing. The demand for inference compute is entirely inelastic right now. Companies are paying whatever it takes to secure reliable uptime.
Because an AI product without inference is just a white paper. It doesn't actually exist.
Exactly. So then we move to phase two, which is from 2028 to 2032. And the narrative in the manifesto shifts entirely.
The goal jumps from $5 billion in ARR to $20 to $50 billion in ARR. And the terminology changes from an inference fabric to a platform empire.
Right. They describe evolving into an AI operating system. This is the transition from being a utility to being an ecosystem. They don't just want to serve the model anymore. They want to orchestrate the entire life cycle.
Managing complex, multi-agent frameworks where specialized models talk to each other.
Pushing lightweight inference down to edge devices. And crucially, deep vertical integration into heavily regulated sectors.
Building specialized compliance layers for healthcare networks or legal verticals. But, okay, this is exactly where I have to push back hard on this entire roadmap.
Okay, let's hear it.
Baseten wants to be the AWS of AI. They want to build an inescapable ecosystem with massive switching costs. But history shows that platform empires often get crushed by the big tech incumbents. AWS, Google Cloud, and Microsoft Azure already exist, and they are not blind.
No, they are very aware of what's happening.
So how does a pure-play infrastructure startup, even one valued at $13 billion today, actually survive a direct, sustained siege by Microsoft or Google?
The threat profile of the hyperscalers is the single largest existential risk to Baseten, because the hyperscalers have infinite capital.
Exactly. Microsoft can just bundle inference. They go to a Fortune 500 company and say, hey, renew your massive Office 365 and Azure Enterprise contracts for the next 5 years, and we will give you all your custom model inference for free.
They can absolutely afford to do that.
They can operate their inference divisions at a multi-billion-dollar loss indefinitely, just to starve independent players out of the market. And all those brilliant software modes we just talked about, the radix trees, the custom C++ kernel software, eventually commoditizes.
It always does.
OpenAI or Meta will eventually open source a compiler that does 90% of what Baseten's custom stack does for free.
You are outlining the exact historical playbook of big tech. You commoditize your complement. If you control the cloud, you commoditize the inference layer to drive more core compute consumption on your servers.
Right. So how do they survive that?
Baseten's leadership is intimately aware of this dynamic. Their survival strategy cannot and does not rely purely on software superiority.
Because the code isn't enough.
No. To reach $1 trillion, to defend against a predatory pricing war from Azure or GCP, Baseten has to pivot from virtual optimization to physical dominance.
They have to own the raw materials.
Exactly. They need an unfathomable amount of physical power and silicon.
Which forces us to look at the terrifying physical math of the AI era. Let's break down the sheer physical requirements outlined in Phase 3 of the roadmap.
Phase 3 covers 2032 to 2036. The target is the $1 trillion valuation.
And to hit that, the projections show Baseten needing to capture 10 to 20% of a global inference market that will reach hundreds of billions of dollars. But to physically support that market share, they will need an active fleet of between 2 million and 10 million advanced GPUs.
The scale of that hardware deployment is it's difficult to process. Let's translate that into revenue.
Go ahead.
Currently, an H100 equivalent or Blackwell equivalent GPU running high-utilization enterprise inference workloads generates roughly $20,000 to $100,000 in annual revenue.
So hitting 50 billion in revenue requires millions of these chips running flawlessly around the clock.
Yes. But securing those chips is no longer just a matter of having the cash to buy them. We are deep into what the industry is calling the compute crunch.
The sources highlight that competitors are already panicking. The supply chain of advanced silicon is tapped out.
The market behaviors we are seeing right now reflect absolute panic. Hyperscalers are executing deals that defy traditional corporate finance.
Like Google. Google is paying $920 million a month, almost $1 billion a month, for 110,000 GPUs.
And Anthropic just committed $1.25 billion a month to SpaceX to lock in capacity at the Colossus data center.
They're paying massive premiums, like 2 to 3 times the spot market rate, for a depreciating asset. Why are they doing that?
Because the cost of overpaying for compute today is infinitely lower than the cost of not having compute tomorrow. It is a risk premium against existential failure.
Right, because if your company runs out of inference capacity, your product degrades, your latency spikes, your users churn, and your enterprise contracts are voided.
You're dead. The hyperscalers are using their balance sheets to systematically corner the physical market. They are panic buying the global supply of digital concrete at a massive markup.
Not just to build their own skyscrapers, but to ensure there is no concrete left for anyone else. It's like a war economy.
It is exactly like a war economy. But the constraint goes even deeper than the silicon itself. Let's play this out. Let's say Baseten manages to secure 2 million Blackwell GPUs. They win the supply chain lottery.
Okay.
Where do they physically put them? The limiting factor of the AI revolution is rapidly shifting from the fabrication of chips to the generation of electrons.
Because you can write the best inference code in the world, but if you don't have access to the electrical grid, your company dies.
Power availability is the ultimate hard cap on the industry. To run a data center housing millions of liquid-cooled supercomputers, Baseten would require tens of gigawatts of continuous power.
Tens of gigawatts. For context, a single gigawatt is roughly the output of a standard nuclear power plant.
Right, and the traditional data center hubs are completely tapped out. You look at Northern Virginia, the Ashburn corridor.
Which is the densest concentration of data centers on Earth.
Exactly. The local utility grid there is exhausted. The PJM interconnect queue, which is basically the wait list just to get a new massive industrial load approved and wired into the grid, is stretching to 5, sometimes 7 years.
You cannot wait 7 years for a utility substation to be permitted in an industry where the entire software paradigm changes every 6 months.
You can't. Which is why the hyperscalers are already buying up nuclear sites, attempting to restart dormant reactors just to guarantee their baseload energy.
This physical reality, the lack of grid capacity, the hyperscaler monopoly on traditional real estate, the massive thermal output of these chips, it presents an existential crossroads for Baseten.
It does. If they stay in the U.S., they are at the mercy of the grid and the incumbents.
So they have to look for power where nobody else is looking, which sets the stage for one of the most unconventional, audacious infrastructure pitches I have ever seen.
And it was a pitch made entirely in public.
Right, on Twitter.
Yes. On June 22, 2026, the exact day, Baseten announces their Series F CTO Amir Hakahite posts celebrating the milestone. And Paramendra Kumar Bhagat, the author of the $1 trillion roadmap, replies directly to him.
With a $500 million pitch. The offer is literally, I offer some of the cheapest compute in the world. Future-proof yourself. Let's talk. He is proposing a $500 million strategic investment into an initiative called Himalayan Compute.
He is seriously proposing that Baseten bypass the U.S. electrical grid entirely and build massive, state-of-the-art AI inference data centers in Nepal.
Are we seriously talking about building multi-billion-dollar supercomputers in the remote Himalayas? On the surface, that sounds completely absurd.
It sounds like a joke. But when you overlay the physical constraints we just discussed, the need for gigawatts of power, the thermal management of the chips, the threat of hyperscaler monopolies, the physics of Nepal, suddenly make terrifying sense.
Okay, let's unpack the brilliant, if wild, logic behind this proposal, starting with the power. Why Nepal?
Because the Himalayas possess vast, untapped hydropower potential. We are talking about massive, high-velocity rivers fed by constant glacial melt and seasonal monsoons.
And the crucial word there is baseload, because I see a lot of data center projects trying to pitch solar or wind energy to hit
Yeah.
sustainability metrics, but solar and wind suffer from intermittency, right?
Exactly. The sun sets, the wind dies. You cannot run an inference cluster serving live enterprise traffic on intermittent power unless you build gigawatt-scale battery backups, which completely destroys your unit economics.
So hydropower provides constant 247 renewable baseload energy. The rivers never stop.
Never. So you have access to gigawatts of cheap, sovereign power that isn't trapped in a 5-year U.S. permitting queue.
Okay, that covers the electricity.
Yeah.
But the second advantage Bhagat highlights is thermal dynamics. These new server racks run unbelievably hot.
Oh, they require complex closed-loop liquid cooling manifolds and massive HVAC overhead just to keep them from catching fire.
And the metric here is PUE, right? Power usage effectiveness.
Right. It measures how much power goes into the facility versus how much is actually used by the computing equipment. In traditional data centers, a massive percentage of your electricity bill is wasted simply running the air conditioning to keep the chips from melting.
So how does the high altitude help?
By building in the Himalayas, the ambient outside air is naturally near freezing year-round. You utilize free ambient cooling. You literally just open the vents. That drastically reduces the thermal management costs of running those liquid-cooled GPU clusters, radically improving your economic margins.
That's also a massive geopolitical hedge, isn't it?
Absolutely. The U.S. and China are locked in an escalating trade war over advanced semiconductors and supply chains. Moving your core physical infrastructure to a neutral third-party nation diversifies your operational risk.
Okay, the thermodynamics and the power availability makes sense on paper, but I need to inject a heavy dose of reality here, because the logistical reality of building in Nepal has to be a nightmare.
The physical friction of execution would be immense.
We are talking about shipping billions of dollars worth of incredibly sensitive, liquid-cooled NVIDIA server racks up winding mountain roads. Are the local highways even rated to handle convoy after convoy of heavy industrial transport?
Probably not without massive infrastructure upgrades.
And what happens when a manifold leaks or a memory controller fails? You need an army of highly specialized, incredibly expensive hardware technicians on site 24/7. You can't just fly a kernel engineer out from San Francisco every time a server rack goes offline.
No, you can't. The maintenance and logistics are severe risks. You are essentially committing to building an entire localized supply chain and technical workforce from scratch in a developing nation. It's a $500 million gamble.
But honestly, my biggest issue is the physics of the network itself. What about the lack of fiber optic connectivity? Baten's entire value proposition, the reason they are worth $13 billion, is extreme, ultra-low latency. We spent half the show talking about shaving milliseconds off the KV cache.
We did.
But the speed of light in fiber optic glass is finite. The physical distance from Kathmandu to a financial server in New York or London introduces an inescapable latency floor of, roughly 100 to 150 milliseconds round trip.
At best.
You can't optimize away the speed of light. So how do you serve real-time AI agents globally from the Himalayas without ruining the latency you just spent billions of dollars to achieve?
That is the critical engineering constraint. And the answer is, you don't. You wouldn't serve live synchronous voice agents directly from the Himalayan cluster to a user in New York.
So what do you use it for?
You utilize edge architecture. You keep your lightweight, highly localized edge servers in traditional US and European data centers to handle the immediate latency-sensitive routing and the initial prompt prefill.
Okay.
But you use the massive, cheap compute capacity in Nepal for asynchronous, heavy workloads.
Oh, like large-scale document processing.
Exactly. Batch video generation, global scientific modeling, massive data ETL pipelines, and background agent orchestration.
I see. It's a vertical integration play. By offloading the heavy, compute-dense tasks to the cheapest grid on Earth, Baseten drastically lowers their blended cost of compute.
Which is the ultimate defense against the hyperscalers. If Microsoft tries to initiate a price war by dropping the cost of inference, Baseten can afford to charge their customers far less than AWS or Google, securing their margins.
Because Baseten's underlying power costs in Nepal are a fraction of what Microsoft pays in Virginia.
Precisely. A gigawatt of sovereign, dedicated hydropower cannot be reverse engineered by a competitor. It cannot be open sourced. It is a physical moat that ensures they are never locked out of the compute supply chain.
It's basically the Henry Ford model. Ford didn't just build the assembly line. He bought rubber plantations in the Amazon and iron mines in Michigan, so no one could ever squeeze his supply chain.
Basin is bypassing the digital landlords entirely. They aren't renting the furnished apartment, they aren't even buying the concrete locally, they are damming their own rivers.
We've traced an unbelievable trajectory today. The architecture of the AI revolution is so often abstracted away as pure software. We think of it as clean algorithms floating in a nebulous cloud.
But the reality of inference is violently physical.
We started at the absolute microscopic level. Engineers writing custom C++ kernels, analyzing the exact clock cycles it takes to move data from a VRAM module to a SRAM core. We looked at the mathematical elegance of FP4 quantization and speculative decoding.
Where a tiny draft model races ahead of a massive neural network to guess the future.
Right. And we watched those micro-optimizations compound into a $13 billion valuation, driving a relentless 10-year roadmap aimed at building the default operating system for global intelligence.
And then that software ambition ultimately crashed headfirst into the hard physical limits of our planet. Millions of GPUs, tens of gigawatts of electricity.
A compute crunch so severe it forces companies to abandon the U.S. electrical grid and pitch half-billion-dollar supercomputers in the shadow of Mount Everest.
It forces a profound reevaluation of what actually constitutes power in the AI age.
It really does. The next time you open an app on your phone and casually ask an AI to summarize a long document or debug a piece of code, take a second to visualize the staggering, invisible chain of events you just triggered.
Your prompt is being routed through cache-aware balancers, encoded into 4-bit quantized matrices, and verified by parallel neural networks.
And somewhere out there, massive liquid-cooled servers are consuming megawatts of power, generating intense heat, drawing down the electrical grid, all just to fetch your answer and beam it back to your screen in a few milliseconds.
The invisible infrastructure of the future is being built right now, and the scale is unprecedented.
It leaves us with a final, mind-bending concept to consider. We tend to view the AI revolution as the ultimate triumph of human ingenuity and software engineering. But if the ultimate limiting factor of this entire boom isn't algorithmic elegance or the supply of the silicon itself, but rather the sheer blunt force physics of generating electricity and cooling hot metal.
Then the map of global power is going to look very different.
Exactly. Does that mean the true superpowers of the AI age won't be software companies in Silicon Valley, but the nations that simply happen to control the Earth's most stable rivers, its deepest lakes, and its coldest climates? It's something to think about. Until next time, keep diving deep.